Hello friends, I'm Ashish and today we are going to learn how to create CMOS inverter symbol, like a symbol for any kind of circuit. And for now I'm considering the CMOS inverter as a reference circuit, and we are going to learn how to do layout for the same. So to do that, let's follow steps. We first of all need to create schematic for our CMOS inverter. So I'll minimize this and I will open up Putty, log in with your e-reader ID password, and the technology we are going to use is 180 nanometer technology. So in order to look all the folders in your directory, type ls and enter into the folder which is responsible for your Cadence 180 nanometer. After that, you are supposed to open Cadence for 180 nanometer. So this command will now open up Cadence for you. So this is your Cadence window, and we can see all the libraries to the left over here, and the libraries which we have created before and which are worked for the simple CMOS inverter and simulation power delay calculation. So we will open up the library which we have created before, that's demo, and this is our circuit which we have created before. And this is just a spec to set. If you want to create your own circuit, and just create new library, create new cell view and give any name, inverter demo I'll say, and type will be schematic. It will ask you for the license and you need to click OK in that, and it will open a schematic, and you are just supposed to design one simple CMOS inverter. So like we have learned in our previous video, just go on placing all the components, select N transistors, NMOS 4, and for NMOS will be keeping the width same. Similarly select P transistor, and we'll be using the 2W, that is double volt for PMOS. And after that we need pins for input, one for output, one for VDD and one for ground. So to get pin, type P and write down all the pin names separated by space. And for our convenience, let's make the direction as input output. So I'll place all the pins now: input, output, VDD and ground. Now just connect all the pins using wires. And don't forget to give the body connections. So click on check and save. As there is no error, you can check for errors always in your command window, and it will show like the schematic check completed with no errors. So you can go ahead with creating the symbol. To create the symbol, click on create cell view, and from cell view give the same name to the symbol, click OK. And now in this step you need to arrange your pins. For a convenience, let the input be at the left let the output be at the right, VDD be at the top, and let the ground be at the bottom. This is just for our convenience, and click OK. This design will open one sample symbol diagram for you. You can edit this diagram, you can delete all the components which you don't want to be in your symbol. I'll delete this, and let's give the part name as in. So on this top window you can see the shapes available, like the circle, polygon, ellipse, line, arc. So we'll go for line. Just draw a simple line and create one triangle, and we need one circle as well. So draw a circle. You can always move the objects which you don't want to be in between your symbol diagram. So let's move this input pin to the input side, the output pin to the output side, VDD be at the top, and ground be at the bottom, and we'll place this name inside the symbol. Once you click on check and save, you are good to go. Your symbol design is ready. So after creating the symbol, we'll be implementing simple simulation, how to simulate these symbolic structures in Cadence. To do that, we need to create new schematic. Let's create one new schematic for the test bench. Let the name be inverter TB. It stands for the test bench. So it will open up one new schematic for you, and now you're supposed to import the previously created symbol. To do that, press I, and it will open up one component list for you. And this component list, while searching the library, find the library in which you have created a symbol, that's demo, and you will find one symbol name, that's inverter demo, which you have created before. And if you move your cursor on your schematic, it will show that symbol to you. Just place that symbol over the body or the schematic. Now this is your component, and the symbol will act as one component, and which is inverter. So now we need VDD, ground, and input output signals. So you can find VDD in analog library, sources, and globals. We will need one more VDD source. I'll tell you its significance later on. And we need ground as well, one for the symbol, one for the source which we will be going to implement, and one extra ground we need. And we need input signal. Let's say it's V pulse. Let the voltage be 3.3, period be 40 nano, 10 pico rise time, 10 pico fall time, and let the pulse width be 20 nano. That's a perfect square wave. And place this symbol, make all the connections, and we need one VDC as well. Let that value be equal to the VDD, that is 3.3 volt. Again, connect it using wires, and in order to measure output, you won't be keeping this output terminal floating. So in order to keep it safe. In order to terminate it, you need to connect one more extra component over there, and that component you can find in basic library and miscellaneous, and that component is no connection. So your schematic is ready. You click on check and save to check for the errors. We don't have any errors for now. Now the significance of this VDC which are connected is that we are using symbolic hierarchy, so the VDD cannot act as one global source, and it fails to provide power supply to all your circuits. So in order to maintain that power supply, you need to connect your VDD to one DC voltage source which is constant, and you need to keep it constant, so that's why you're using DC voltage source, and the value of source is equal to the VDD, that is 3.3 volt. And once you are done, you are good to go. You are ready to launch your ADL and simulate the circuit. You need to select your simulated directory, that's Spectre, apply and OK. Again, select your model libraries for 180 nano. Go in this folder. These two are for your model libraries for your NMOS and for PMOS. Click apply and OK. And now you are supposed to select your analysis. Let's select one transient analysis for, let's say, 200 nanoseconds. Make sure you enable your analysis over here. You check in over here. Click apply and OK. And now you will be plotting your input and output. So click on output to be plotted and select on design. Select the input and output net and run your code. So it will generate one netlist file for you. This netlist file contains all the values, all the voltages, capacitances at the nodes, including the gains. And if you open up the window, waveform window, you can find input with respect to output, and you can see the perfect inversion occurring over there. So like this way you can create your symbol and simulate it. Especially this method is useful for the larger circuits in which you are implementing a lot of symbols, a lot of structures. So likewise you can implement and simulate the symbols in Cadence. Now we are going to discuss how to create a layout and how to find out the LVS check and extracted circuit. So that will be in the next part of this video. This is the stage where we are going to implement a layout, and to implement a layout, let's create one schematic for the CMOS inverter very quickly. Let the name be inverter, and just follow all the basic steps. Select your P transistor, select your N transistor, and select NMOS in the similar way. Select NMOS 4, and place your NMOS. Very quickly join the floating terminals with wires. We'll keep one wire for input, output, one wire for input, one wire for VDD, and one wire for ground. And in this case we need to consider each and every pin, each and every input, each and every connection in order to carry out the LVS match. So we will give pin connections to the body of PMOS and body of NMOS as well. So right now we'll be giving pins. So to do that, per type P, Let's give the pin names: input, output, VDD, ground, and let's say the body for PMOS is BP and body for NMOS is BN, and let the direction be input output, and just place pins over there. VDD, ground, body for PMOS and body for NMOS. And you also need to take care about the sizes of your PMOS and NMOS which you selected. For NMOS, you can see the width is 300 nano with the multiplier of 1. M indicates the multiplier, and for PMOS you need to make the size double than NMOS, so let's make it 600 nano. So you are good to go with your circuit. Now you will creating your layout. So to do that, go to file, new, cell view, and create the cell with the same name, but give the type as layout. Your type will be layout, and click OK. It will ask you for the license, then click on yes, and this design one will open up one layout window for you. And to the left side you can see the different layers, that is P well, N well, active, T active, N active, P active. Likewise the polysilicon, metal, these all layers are useful while drawing the layout. And this indicates the actual view, like the contents which you want to be visible, which you don't want to be visible, you can always select. And it's not that difficult to draw a layout for any kind of circuit. You just need to have components placed like well in order. So let's get one NMOS. So to do that, press I, and you need to browse that instance. Click on browse, and now you need to find out the technology library file, that's NCSU TechLib TCMC.02. that's the technology library for 180 nanometer. And you can find different cells, that is M1N, M1P, M1 poly, M21, M1, M3, M2. So among those you need to select PMOS. So click on PMOS, and on the right side you can see the layout. So once you minimize it, you will see one design for PMOS. You can choose the size of your PMOS as well. It should be the same. Let's say it's 600 nano, and just place your component. Similarly, you need to have your NMOS. And you have got a NMOS, keep it right below your PMOS. So if you want to check the distance, if you really want to check the width of polysilicon is like the minimum which is provided by technology or not, so to do that, press K. You will find one scale over there, and you can always measure the width over here. So let's say it's showing 0.2 micro. That's the minimum width of technology provided. It's 200 nano. Even if you want to check it for your PMOS, if you want to check the width of your channel, you can always go for it. Now you need to short this gate of PMOS and gate of NMOS. So to do that, we need to add one path. So type P. It will ask to you to create one path and select polysilicon from the left window, and you can see it will automatically select the minimum width is 0.2 micrometer, and make sure you draw the same number of nets which you are drawn in your schematic. So just connect these two terminals, and let's take one connection out for our input. Now we need to connect the drains of PMOS and NMOS. So you can choose any side which you want to be drain or which you want to be source. So for our convenience, we'll be selecting the right side of PMOS of as is a drain and right side of NMOS as drain. So again, to connect those, select the metal one from the left list. Again, type P. So it will show you the option to create path, and that path will obviously the metallic path. So select on this, click on the design and drag it till the drain of NMOS and leave it here. So now till now you have sorted your drain. Now you need to give like VDD and ground connections. So for the PMOS, the left side is source, so we will take out one metal connection from the pin, and that connection will act as VDD. Again, the left pin from NMOS is the source for NMOS and which is to be grounded. So for now we have created the layout for our required design, but we are left with two more things, and that's the body for PMOS and body for NMOS. So to create this body, you need to click on create and via. For PMOS, the body will be N type only. The N type, that's the name for your PMOS connection. Make sure you keep it adjacent to your PMOS structure. Again, click on create via, and for NMOS, your body will be M1 to P type. Just because you have got a P substrate, you need to connect your metal to P type, and which will act you as your body. Again, place it somewhere near. Now you need to add one connection over here, and that connection is your metal to the polysilicon. So again, click on create via and select the via definition as metal 1 to poly. Make the rows and columns to be 1. You can always adjust the length and width of your connection depending on the size of your polysilicon. So make sure you just keep that contact here. And yes, you are supposed to always verify the design rules. So to do that, click on verify and DRC. It will pop up one window. Just click OK. And for now there is no design rule check error. If you want to check whether you have got design rule check error or not, always open up your command window and it will show you the summary of rule violation cell inverter. Total errors found 0. That means our design is correct in terms of the design rules. Now you need to create the contacts which you have created in your schematic. That's input, output, VDD, ground, body for PMOS and body for NMOS. So to do that, click on create and pin and write the names same as in your schematic. Let's say N in, out, VDD, ground, body for PMOS, body for NMOS, and make sure you click on create label, and you can always select option for your label. Let's make the height as 0.2 and click OK. Once you click on height, it will start the pin mode, and you just need to select the part from the metal in order to draw the pin. So hide it. So our first pin is input, so this is your connection which connects your polysilicon from the metal one, and yeah, obviously the pin will be in the metal one format, so just create one small connection over there. So this is your input. Also you need to draw the output. This is your output. This will be your VDD. This will be your ground. This will be your body for PMOS, and at the last, this is the body for NMOS. So for now we have completed with our layout, and in order to check the design rule, again click on verify and DRC. You don't find any error. Total errors found as 0. So you are done with your layout structure, and right now you need to extract your layout. It will extract all the components, all the nets, all the pins which you have implemented in your layout, and the same extracted circuit will be compared with the actual schematic. So in order to extract, click on verify and extract, and just click on OK. So you can find the extracted version of your layout in your library. Under your cell name inverter, you can see the extracted name. If you double click on it, it will open up one view for you, which is the extracted view. And if you press Shift K, Shift F, it will show the actual front view of your extracted view. You can find all the pins, all the sizes, and all the layout connections which are made. So open your layout, and now we'll be comparing your layout with the schematic, that is the LVS layout versus schematic match. And once you find your LVS match, your layout is correct and it is ready to go for the fabrication. So in order to do the LVS match, click on verify LVS, and it will ask you to extract your schematic and extracted view. They're just the same. You just need to click on the run button in order to begin the process. So just click on run. Once you click on run, wait for a while till it gives you the result. And yes, we have the result as the LVS job has completed and netlist match. That means our LVS is matching and the layout is perfectly matching with our schematic. So it is ready to go for the fabrication. Click close. If you want to check all the nets, all the nodes, just click on the output, and you will see one netlist file. You can see all the terminals which are on layout and all the terminals which are on schematic, and you can see the exact match. You can always find there is no unmatch, and all pins are exactly matching with each other. Total terminals are same, so that means our netlist is matching. and we don't have an error for now. If you have any error in your netlist file, you can always find the errors at the bottom over here, and you can compare your schematic design with your layout in order to see what is not matching. So likewise, you have completed your LVS layout and you are good to go for the fabrication. Thank you for watching this video. We can meet in the next video. See you.